Hello there, Mr. Sutton, bringing you this lesson on integration by parts. In this one, we're going to be evaluating integrals, both definite and indefinite, of products using integration by parts. For the warm-up on this one, pause the video and see if you can strategize how to integrate this expression. Alright, so you probably hit a brick wall here. We can't really simplify this in any way, and we also can't use substitution. There's no function, inner function, and its derivative hanging out in here. So when simplifying and substitution don't work, and this certainly isn't a partial fractions kind of situation, we have something else called integration by parts. So this requires that we have two things being multiplied together, and here's how it works. First step we're going to do is write the integration by parts formula, which is integral of u dv, which u and dv, those are both just functions, like x and e to the x dx. So that's going to equal u times v minus the integral of v du. Now, if you're wondering where this formula comes from, this is actually just the product rule if you were to integrate both sides of it and move things around. Like this is the uv that you're taking the derivative of a product. This over here is the uv prime. Over here is the u prime v. But you don't really need to know that in order to use it. What we do need to figure out is all these different parts, u, v, dv, and du. So our next step is going to be to choose our u and our dv. It isn't necessarily the order they're written in up here, although let's go ahead and try the order they're up here. You have to choose them very consciously, and we'll talk about how to do that in a little bit. But for now, I'm going to let my u value be x. And then I'm going to let my dv be e to the x dx. All right. And by the way, the dv always has a dx attached to it. Like if you picked x as your dv, you'd still need to have the dx there. Anyway, next step, we are going to differentiate u. That's how we're going to come up with the du you see in this equation. So the derivative of x, that's just going to be 1, but we're also going to put a dx next to it since we just differentiated an x. It's kind of like implicitly differentiating. And we also see that we have a v kicking around in this equation. So that means this dv needs to turn into a v by integrating it. So the antiderivative of e to the x, that's going to be, well, also e to the x. So this is a fairly nice example to start with here. Next step, we're going to plug all of these things into this formula here. And that's why I always like to write the formula first. So we've got u times v, so that's x times e to the x. And then we have minus the integral of v times du, so that's minus the integral of e to the x times 1 dx, which is just e to the x dx. And by the way, you might have noticed that this makes a nice little 7 if you do it the way I've got it laid out. And I only noticed this because I had a student named Dante who he thought the answer to every question was 7. So this one's for you, Dante. Follow the 7 when you're plugging in here. All right. So our next step, we actually have to take the integral of e to the x. We've only kind of partially digested or partially integrated this equation, or this expression. So our next step, we have to integrate the v du part, and the antiderivative of e to the x dx is just e to the x. So this is going to be x times e to the x minus e to the x, and don't forget your plus c. The plus c you can put in at the very end after you've gotten rid of that last integral. Before we move on to a new example, let's ask what would have happened on example 1 if we had chosen u and dv differently. So here is example 1 again. Let's say that instead of choosing x for u, we chose e to the x. And let's say we made our dv value be x dx. Well, in that case, you would have a du of e to the x dx, and a v of, now we have to integrate this would be 1/2 x squared. And then multiplying it out, plugging in, we would have, following the 7 here, this would be 1/2 x squared e to the x, minus, going this way now, the integral of 1/2 x squared e to the x dx. And at this point, you're like, okay, now I just need to take my antiderivative over here. But this expression here, this is actually even worse than what you started with. So if you're getting a worse integrand, you've probably chosen u and dv wrong. So let's talk about how we can be a little bit more strategic about this. In general, the u value that you're choosing should get simpler or at least no worse when you differentiate. And the dv value you choose should get simpler or no worse when you integrate. So we want a u value that gets nicer when we differentiate, a dv that gets nicer when we integrate. And there's actually a general preferred order for picking function types in. And I have the acronym LATE here for how you should pick the u value. So the L stands for logarithms. Logarithms, those are pretty easy to differentiate. They're a real pain to take the antiderivative of, so we should make our u value logarithmic if we have a choice, because we don't want to have to integrate this one. The A stands for algebraic. This is basically anything that can be written as x to some constant. So those aren't too bad to take the derivative of. We don't like to take the integral of those because the exponent just keeps getting bigger, but if we have to choose between that and a log, I guess we would go with logarithmic. The T stands for your trig functions. And then the very last thing that you want to choose for your last resort is E, exponential. Exponentials, I mean, they're not that bad to take derivatives of. The reason they're at the bottom of the list is because they're also not that bad to take integrals of. If you have a choice, you want to take an integral of an exponential. For this next example, we're going to try to find the definite integral of this expression from 0 to pi. Now, this is an integration by parts situation, again, because we have two functions being multiplied, and substitution and simplifying won't work. But we have the extra hurdle of having to do this definite integral. So, as luck has it, there's an IBP definite integral formula that we're going to use. So this is going to be, if you have the integral from a to b of u dv, that's going to equal uv inside an evaluation box from a to b, minus the integral from a to b of v du. So it's pretty much just integration by parts, but eventually we're going to plug the limits in, and basically anything that's not inside an integral is inside an evaluation box, and in both cases, you've got these limits of integration kicking around. All right, so pause the video and see if you can find all the different parts and plug them into this formula. All right, so for picking my u value, I have a choice between an algebraic and a trig function. A comes before t in late, so I'm going to go with algebraic. So 7x is my u value. And then dv is going to be sine of 3x dx. Now for the du, that's going to be 7dx. And for v, antiderivative here, well, that would normally be negative cosine, but we have an inner function of 3. So that's going to be negative 1/3 cosine of 3x. Plugging everything in now. We've got, follow the 7 here, so we have negative 7x over 3 cosine of 3x. That's the uv part. And we're evaluating that from 0 to pi. Next, for the integral part, we've got, let's see, multiplying these together, we've got negative 7/3 cosine of 3x, but we're already subtracting that integral, so negative is going to be a positive integral from 0 to pi of 7/3 cosine of 3x dx. At this point, we still need to take the antiderivative of this piece here. So we've got this original evaluation box plus now taking the antiderivative here. This is going to be, let's see, sine of 3x, but we have to divide by 3. So this will be 7/9 sine of 3x, again from 0 to pi. And at this point, we're just plugging everything in. Now, one way of doing this is to do these evaluation boxes separately, and that's how I'm going to do this problem. But since they have the same limits of integration, you actually could make this one big evaluation box with this term just plus 7/9 sine of 3x. So do it however you want. But doing it the way that I have laid out here, we've got all this stuff with pi plugged in, and we're going to have to figure that out in a minute. And then we have all this stuff with 0 plugged in. Now, I'm not going to bother writing all of it out because if you plug 0 in for the x here, that zeroes out everything. I'm just going to write minus 0 here to kind of note to myself that I did something over there. Next, evaluation box, we've got all this stuff with pi plugged in. But now the sine of 3 pi, that's really like the sine of 1 pi, which is just 0. And then if I plug 0 in here, sine of 0 also comes out to 0. So when the dust settles, it's really just this first term that's going to give us anything unique. And let's see here, cosine of 3 pi, that's like cosine of 1 pi, which is negative 1. So when the dust settles, we have positive 7 pi over 3. We're going to do one more example. In this one, we have a table with selected values of the twice differentiable functions f and g. And we've got some other stuff for g as well. They gave us a little extra for g. Now, if f prime is 3, we want the value of integral from 2 to 4 of f of x g double prime of x dx. All right. So pause the video, and in light of everything we've just covered with integration by parts, see if you can get to the bottom of this one. All right, so hopefully you realize that this is an integration by parts situation. We have two functions being multiplied, f and g, and there's no way to use any kind of substitution on this one. Certainly we can't simplify this because we don't even know what f and g really are when it gets down to it. So it's integration by parts or nothing on this one. So let me write out my definite formula here for integration by parts. And now picking a u and a v value. Now this is where we don't really know what kind of functions these are, so using late isn't going to be helpful here. We kind of have to know the deeper meaning behind all that, which is that we want our u value to be something that we don't mind differentiating, and we want the dv value to be something that we don't mind integrating. So taking a look at the different options here, let's say that I chose f of x for my u value. Can I take the derivative of f? Well, I kind of can, because they told me that f prime up here is 3, so we know the derivative of f. Let's say that I picked g double prime as my u value instead. Do I know the third derivative of g? Well, I don't. There's nowhere they told me that. So really, I don't have a choice. I'm going to have to pick f for the u value, because I know its derivative and I don't know the other derivative. That means that by default, g double prime x dx is going to be our dv value. But fear not, this is actually going to work out pretty nicely. So taking our derivative then of the f function, that's going to be du equals f prime of x, which we just saw was 3. And then, so that's a 3 dx. And then over here, taking the antiderivative of g double prime, well, actually, that's pretty easy. That's just g single prime. Okay, putting it all together, we've got evaluation box here, f of x times g prime of x, evaluated from, they said, 2 to 4. And then we also have minus the integral of 3 g prime of x dx, evaluated from 2 to 4. Let's go ahead now and take the antiderivative of this one here. And right after I do that, I'm going to put it immediately in the same evaluation box as these two here. So I have the original stuff that was in my box, f of x times g prime of x. And now, what else is going in there? Well, the antiderivative of g prime is just going to be g. So this is going to be minus 3g of x, evaluated from 2 to 4. All we have to do at this point is plug in 2 and 4 and see what happens. So I've got 4 plugged into all that stuff, minus 2 plugged into all that stuff. And now it's all about looking things up in the table now. F of 4, that's right here, that's 13. G prime of 4, that's right here, this third row, second column, that's 7. Minus 3 times g of 4. G of 4 is 9, so 3 times 9. And then over here, f of 2, that's going to be 7. And then we have g prime of 2, that's 1, getting multiplied by the 7, minus 3 times g of 2, which is 3 times 2. So this is, let's see here, 91 minus 27, which is 64. Over here we have 7 minus 6, which is 1, and we're subtracting that. So 63 when all is said and done. So that's it for this one. I think you'll agree that parting is such sweet sorrow. Until next time, Mr. Sutton signing off.